Hi, I'm Scott Knockleby. In this video, we're going to look at Jacobians for spatial manipulators. So by the end of this video, you should be able to understand the two methods for determining the Jacobian for a spatial manipulator. So for planar manipulators, we previously showed that our velocity of our end effector is equal to the Jacobian, matrix J here, times our vector joint rates, as well as our torques, is equal to the Jacobian transpose times our wrench. All right, now this is the static force case. And we showed that the Jacobian, each column represents one joint of our robot, and to determine each column, you take the partial derivative of x with respect to theta I. All right, and so typically for a 3-joint robot, this would be a 3x3 matrix. Now for the spatial case, our formulas are still the same. Our velocity is equal to the Jacobian times q dot, and our torque for the static force case is equal to J transpose times F. All right. The difference is we can't just use this formulation to find our Jacobian because we have 3D rotations. All right, we're not in the plane. So we have to look at a different way to find the Jacobian. All right, and as well, we can define our velocity in this case of our end effector has 6 components, 3 translational in the x, y, and z direction, and 3 rotational, which are the angular velocities about the x, y, and z axes. All right, and so we have a translational part and we have an angular part. As well, our wrench, F, in this case, will have 3 forces in the x, y, and z direction, as well as 3 moments about the x, y, and z axes. So we're going to look at how we can find this Jacobian for the spatial case. And there's 2 approaches for doing that. All right, so we have 2 methods for finding the Jacobian for spatial manipulators. The first method is using joint directions and derivatives. And the second is using joint directions and cross products. And you can think of this sort of as, basic mechanics approach. So let's look at the formulation for each of these. All right, so if we're using joint directions and derivatives, if we were to draw sort of a schematic of our joints, suppose we have Z1 here, we have Z2 over here, and then maybe Z3 is over here, and then suppose we have a spherical wrist, so we'd have, say, Z4, Z5, Z6, and then maybe we have our end effector point here. All right, now for the angular part, in terms of the angular velocity of our end effector, which is omega, it's simply just going to be the summation from I equals 1 to n, or whatever number of joints, but in this case we have 6 joints, of omega I, our joint rate of joint I, times the joint direction, Zi. All right, and our translational will just be the partial derivative of our x vector with respect to joint I. So our Jacobian then becomes of our end effector point with respect to some reference frame, and again, just like for the planar case, each column of the Jacobian represents one joint of the robot. So if our ith joint is a revolute joint, our ith column of our Jacobian will have this form. All right, so we do the partial derivative of x with respect to theta I, joint I. That gives us our translational components. And then here's our joint direction, zi, for joint I, which will give us our angular components. All right, so we use that for revolute joints. Now, if, say, joint J is a prismatic joint, we're going to have no angular component here. So this will be a 0 vector, 3 by 1. And we'll just simply have our translational joint direction for the translational part. All right, so we can make a note here in the above. I denotes a revolute joint. J denotes a prismatic joint. And our vector x ref here is just simply our position vector from the origin of frame 0 to the origin of the end effector frame in terms of whatever reference frame we're using. All right, so this is one approach. And in a subsequent video, we'll show how you use this method to find the Jacobian for a spatial robot. Now let's look at the second approach. All right, so in this approach, we're using joint directions and cross products. All right, so you can think of this as, just using basic mechanics. So in this case, we'd have, say, a coordinate frame we can establish. And this would be our reference frame. And we may have a prismatic joint. This would be ZJ, say. And we could have a revolute joint, ZI, which has a joint rate of omega I. And then maybe we have our end effector off of that point. All right, and the vector from joint I to the end effector, we're going to denote as R from the origin of frame I to the origin of our end effector frame. All right, and that's going to be with respect to our reference frame. And we can actually make a note, these are all with respect to our reference frame. Okay, so now for a revolute joint, our velocity of the end effector point due to our angular velocity is just simply going to be our angular velocity omega I cross our position vector R. All right, and now omega I vector is just omega I magnitude times our joint direction, and we can write out our position vector. So it's from the origin of I to the origin of the end effector frame. All right, and this is the same, omega I is the same as theta I dot. Okay. So that is the translational point or component of our velocity on the end effector due to our rotational joints. All right. Our revolute joints also obviously provide an angular velocity. Which is simply omega I, which is the omega I component, or magnitude times Zi, which is the same as saying theta I dot Zi. All right, and so these are the translational and the angular components due to our revolute joint. We can also have a prismatic joint. All right, and so the translational velocity due to our prismatic joint of our end effector, which is d dot j. It's just going to be the magnitude of our joint rate, our translational joint rate, times the joint direction. All right, and then the angular component due to our translational joint, well, they don't contribute any angular velocity. So it's a zero vector. All right, so again, a revolute joint, and J is denoting a prismatic joint in this case. So we can write this out in matrix form. Again, each column of our Jacobian is one joint of our robot. So if our ith joint is revolute, we have this formulation. That's the translational component. And then we have our angular component in the bottom part. And then if our ith joint is, our jth joint is prismatic, it will just be Zj here. And we'll have a zero vector in the bottom. Again, let's just make a note where I denotes a revolute joint. J denotes a prismatic joint. Now either formulation, either this formulation or this formulation, will get you your Jacobian, right? They'll return the same Jacobian, right? It's just two different approaches. And we'll also look at an example of how we use this method to find the Jacobian for a spatial manipulator in a subsequent video.